This lecture will focus on the boundary conditions for diffusion problems. So hopefully from our previous discussion on fluid motion, like blood flow in a capillary wall or Passoyer flow or boundary layers, etc. So you have heard about the boundary conditions for a lot. And I mean, hopefully for now, you recognize the importance of boundary conditions, of course, also initial conditions. If not, then this is the time to let you be aware that these are physically or from like physical modeling or practical purpose, they are extremely important. Whenever you have a differential equation, no matter it's an ordinary differential equation or partial differential equation, you need a boundary conditions or initial conditions to set up your problem. So it's good to have the habit of always looking for boundary and the initial conditions for all the physical problems that you encounter. So before we talk about the boundary condition, let's just briefly mention initial condition. So if in a physical process that is time dependent, or you have differential equations that involves time derivative, differential equations of time derivatives. In this case, you need initial conditions. So initial conditions is written for all the spatial domain, but at t equal to 0. For example, e.g. for concentration of species A, it is of all x positions at a time equal to 0. You prescribe it as initial value C0. This is for all x positions. So C0 usually, we use C0 to refer to initial condition, or at a time equal to 0, or just a constant. So in most cases, the initial condition would be a constant, means it wouldn't be spatially dependent. You may have a uniform concentration to begin with. And if there is no solute at the time equal to 0, or you start to introduce solute at the time equal to 0, but before time equals to 0, there's nothing, then you would have initial concentration to be 0. So this is what happens at time equal to 0. Now for boundary conditions are for at one particular spatial location, but for all time. So boundary for specific spatial locations. Let's look at three types of boundary conditions. The three types of boundary condition, we are now discuss these in the context of like a diffusion problem or biotransport. However, these three boundary conditions are mathematically generic. Means there are three types of, like mathematicians categorize three types of boundary conditions, and we will discuss one by one. And our discussion is in the context of diffusion and concentration. So the first type of boundary condition is specify the concentration at the boundary. For mathematicians, this is the first type of boundary condition. So specify the concentration means at one given boundary, the concentration is given. So this can happen at a surface. So for example, if in the surface of a plate, you are saying, I prescribe the concentration on the surface. Let this surface be, like for example, this is your X position, this is your Y position. And now, in this case, your concentration of solute A at Y equal to 0, this is on the plate, at all time T is a given at CAS, S means surface. So this CAS is known, or we call it prescribed. So it's a given condition that so that you know on this plate, it's always maintain this concentration at the CAS as a constant value. It can also happen that if on the surface, if you have some disk, for example, it's a drug pill, and like for pharmaceutical purpose, or maybe you can think about it's a sugar, maybe it's also fine, a candy. So then you put it in water, maybe a glass of water, and this will dissolve to the water. And because of the maximum solvability of solute in water, for example, let it be a candy. So the sugar has maximum dissolvability in the water, and we would assume on the surface of this candy, or on the surface between the candy and the water, the concentration is a constant. This is given by the maximum solvability of sugar in water. So this will be the concentration of sugar in water on the surface of this candy. So this is another example that you may have specified the concentration at the boundary. And the reason we call the first type mathematically, it means what you are given is the value of the variable itself. So the variable we are looking at, the primary variable is concentration. So the variable we are interested in is the concentration. So we call the primary variable. Now the boundary condition is given for the variable itself. It will make more sense when we talk about the second type of the boundary condition. You will see what does it mean itself versus not itself. So here it means we prescribe the boundary condition for the variable we are interested in or we would like to solve for. Second type of boundary condition in the context of diffusion is called the zero solute flux at the boundary. Mathematically, this is the second type of boundary conditions. The zero solute flux, it is usually applicable under two conditions. One is the boundary is impermeable to the solute. Boundary is impermeable to the solute. For example, you have a tank, and while the solute can diffuse within the tank, it can go anywhere. However, the boundary of this tank is impermeable to the tank. So you can put X copy Y. Have length Lx, width Ly. So on any of y equal to 0, y equal to Ly, and x equal to 0, and x equal to Ly, on these four boundaries, the particle cannot penetrate through the boundary. That means when the particle hits the boundary, it cannot go through, it can only bouncing back. And that means whatever goes through the boundary would be 0. So the flux across the boundary would be 0 flux. Then we use Fick's first law. So we have flux is, let's say on a y boundary or along the y direction, AY equals to minus DAB partial CA partial Y. Now we have 0 flux at the boundary. Means NAY on the boundary, for example, let's say at y equal to 0, would be 0. Then the corresponding boundary condition would transfer to partial CA partial Y evaluated at y equal to 0. Now this is our boundary condition. We call it a second type. This is because the boundary condition is written in terms of the derivative of the variable instead of the variable itself. In terms of the derivative of the variable. Now here we are talking about the 0 flux. And then we have flux equal to 0. other scenarios, you may have a prescribed flux. Maybe you know what's the flux value. Then you would have non-zero flux, but you still know the flux. You still know the derivative of your primary variable. That would still count as the second type of boundary condition. So the second type means it's written in terms of the derivative. But for our discussion, we just talk about, we will limit ourselves to zero flux. So the first scenario is boundary is impermeable to the solute. The second possibility that is relevant in our discussion is when the boundary represents a symmetry plane. We will have those type of like applications when we talk about transport in a body in a tissue. So the second is boundary represents a symmetric plane. Example, if you have like a plate, everything, all the extracellular, not extracellular, all the environment around the plate, above and below, they are all symmetric, and this is the symmetry line. So in that case, you can say everything like is a mirror reflex of this center line. And in this case, the flux would be zero. So if you ask what's the flux across this boundary, across this center line, you will have zero flux. So you will have partial CA, partial, let's call it, just call it Y, partial Y. This is Y equal to zero maybe. This is the symmetric boundary condition. And although we haven't been talking about the symmetrical diffusion scenario, but if you can recall Pasolyev law, we know that D, B, DZ, this is the Pasolyev law. Sorry, not D, DVZ, DR. DVZ, DR at R equal to zero. It is equal to zero because it's parabolic, and along the center line, it's symmetric. There's no gradient, it's flat. And this is also why the shear stress is zero at R equal to zero. Because the fluid velocity is symmetric, there is no relative shear motion. And that's why we don't have shear stress. So these two scenarios, like, they are the same in terms of if you have a symmetry line, then if you treat the symmetry line as a boundary, then the flux along the symmetry, or if it's velocity along the direction you're looking at, would be zero. So this is the second boundary condition we called zero flux in our context. The third boundary condition here in the context of transport, we call it convective transport as the boundary. Convective transport at the boundary. So this is mathematician called the third type of boundary. So let's look at a scenario this is applicable. So for example, if you have some plate, and you know that if you have some concentration, either prescribed or you need to figure out whatever, you have the concentration, let's call it y. Now this is x. This is y equal to 0. So you would have a concentration at y equal to 0. And you would also have a concentration which is at the bulk particle. Now this Ca bulk. Bulk means it's away from the boundary. And you may have some fluid flow. And when we talk about the boundary layer, we know that if you have a fluid flow generate along this direction, you would have like a fluid boundary layer. And then because of the boundary layer, and because of the fluid motion within the boundary layer, then you will provide a convection, because we know that within the fluid boundary layer, you have both Vx as a function of x and y. You also have Vy as a function of y, fluid velocity. So you would have fluid being in both x and y direction. So if you think about the convection, the convection along the y direction, then you do have a fluid velocity along the y direction. That will be like the bulk velocity of the solvent. And so now you may have diffusion and convection happen together. In this case, right on the plate, we only have diffusive flux. You may wonder why we only have here is y equal to 0. We wonder why we only write a diffusion term, no convection term. This is because of the non-slip boundary condition. Right on the plate, the fluid velocity is 0. That's why right on the plate at y equal to 0, you can only have diffusion. You don't have convection. But once you are away from the plate, even a tiny bit away from the plate, you can expect convection to happen, but that will contribute to the convection from the surface to the bulk. So that means the flux due to the diffusion right on the surface, due to the conservation of mass, how much you leave from the surface would be the same as how much you leave just a one layer above the surface. And this will given by Km. Km we will define what it is. Ca at y equal to 0 minus Ca bulk. So Km is called the mass transfer coefficient. Dimension of Km is length per time. It's the same as velocity. So the right-hand side, which is Km, a mass transfer coefficient multiplied by the concentration difference between the surface and the bulk. This means it's another way. This convective isn't the same as exactly the same as the convection we discussed in the last lecture. This is more referred to how fluid layer would contribute to the diffusion or the contribution to the flux, which is also the same as the diffusion value, because this equation, the left-hand side equal to the right-hand side. This tells the amount of things being diffused would be proportional to the concentration difference between the plate and the bulk. So the concentration difference, which is Ca minus Ca bulk, this difference is the driving force for these flux. Driving force of flux. Of course, it's the same as, not the same, like you can approximate as this, but this is also a driving force. These two are related. They are related exactly by this boundary condition, by this equation. And this Km, it depends on multiple factors. So it depends on the geometry, of the flow, of the surface, and also physical property of the fluid. Physical properties. Fluid. And whether it being laminar flow or turbulent flow also matters. It depends on multiple conditions, but all related to the flow behavior and the geometry. So the reason we call it the third type of boundary condition, and this is the boundary condition as you see the equation. It is a boundary condition that relates to both the variable and the derivative of the variable. So in the dc dy term, you have a derivative, and on the right-hand side, you have the c evaluated y equals to 0. So this is a boundary condition. In both the variable and the derivative of the variable. So here we are just considering like a one direction, like along a y direction or along any direction I'm looking at. Then we have these three types of boundary condition. And then in a more complicated scenario, you may have diffusion along multiple scenarios. You may have like along x, y, z, maybe along the x direction, you have the third type of boundary condition. Along the y direction, you have the second type of the boundary condition, or etc. So you may have a hybrid multi-directional transport conditions. That can happen. You just keep in mind that what we are talking about is the three type of boundary condition means the nature or the mathematical nature of the three behaviors. They can also be mixed in along different directions. So these are the boundary conditions, and I would suggest you also revisit your like differential equation classes and to see like how boundary and initial conditions were discussed in that context, and that may help you to connect to this class and help you appreciate why boundary conditions and also initial conditions are a big deal. Okay, let me read you guys an exercise. Explain why a zero flux condition arises to the center of planar bed or cylinder or cylinder basically it's a conceptual understanding or like clear your thoughts on why the zero flux diffusion boundary condition is a condition for any problem with symmetry. Right, that's the end of this lecture.